Hello teachers, let's talk about the last section in chapter 6. It's section 6-4 where we talk about proportional reasoning. When you finish this section, you will be able to understand and explain ratios and their relation to rational numbers, proportions and their properties, the constant of proportionality, scaling, and bar models. So, ratios. What is a ratio? A ratio is used to compare quantities, usually written as A colon B or the fraction A over B. And if you're going to use it for calculations, the fraction or the rational number A over B is better than writing it A to B. I've even seen it written with the word 2, so A to B. It's used to represent part to part, part to whole, or whole to part comparisons. So let's do an example. There were 7 males and 12 females in the Dewdrop Inn on Monday evening. In the game room next door were 14 males and 24 females. We're asked to express the number of males to females at the inn as a ratio part to part. Alright, so how could we do that? Express the number of males to females at the end as a ratio part to part. Now, the number of males is 7, so we have 7 males to 12 females. That's what they have in mind here. Now, you can reduce that fraction if possible. Okay, so whenever you set up a ratio in fraction form or rational number, it is appropriate to reduce it to lowest terms, or we talk about completely simplified. Second question, express the number of males to females at the game room as a ratio. So at the game room, listed second here, we're 14 males to 24 females. But the difference between these two ratios is 14 over 24 can be reduced. They both can be divided by 12. And you have by 2. 14 divided by 2 is 7. And 24 divided by 2 is 12. My brain was ahead of my mouth. Notice this is exactly the same ratio. So even though there were different numbers in the Dewdrop Inn versus the game room, it is the same ratio of males to females. And typed up, we have our answer 7/12 for the first one, and then 14 over 24, or 7/12 for the second one, just like we said. Now there's a part C. Express the number of males in the game room to the number of people in the game room as a ratio. And this is a part to whole ratio. So back to the game room. I'm going to underline that. 14 males and 24 females. And so we want to do the males to the total people in the game room. So there were 14 males. In total, there were 14 plus 24 people. So you have 14 divided, and we know 14 plus 24 is 38. Again, this fraction should be reduced. Both of those values divide by 2 or divisible by 2. So I could write 14 as 2 times 7. I could write 38 as 2 times 19. Of course, the 2's cancel to give me the ratio 7 to 19. So there were 7 males to 19 people in the room. And you see, there it is simplified. Now, we know what a ratio is now. What about a proportion? Well, a proportion is a statement that two given ratios are equal. Notice it says if A, B, C, and D are all real numbers, and B is not equal to 0, and D is not equal to 0. Why would we say that? Because notice they're in the denominator down here. Then you can say the proportion of A over B to C over D, or A to B equals C to D, is true if and only if, notice what we did, AD is equal to BC. So AD, you cross this way, is equal to BC, and you cross that way. And that's how you can tell if a proportion is true. It's also how you can solve for missing values of a proportion. All right, so we have an example. Allie and Bente type at the same speed. Allie starts typing first. When Allie had typed 8 pages, Bente had typed 4 pages. So when Bente has typed 10 pages, how many has Allie typed? And they go on to say this is an example of an additive relationship. So you should look out for this. Students should reason that since the two people type at the same speed, when Bente has typed an additional 6 pages, Allie should have also typed an additional 6 pages. Again, what's terribly important here is they type at the same speed. So again, Allie got a head start. When Allie had typed 8 pages, Bente had typed 4. So she was 4 ahead the whole time. And again, when Bente has typed an additional 6 pages, Allie should have also typed an additional 6 pages. So she should have typed 8 plus 6 or 14 pages. It says Carl can type 8 pages for every 4 pages that Dan can type. If Dan has typed 12 pages, how many pages has Carl typed? This goes on to say this is an example of a multiplicative relationship. So they don't type at the same speed. Carl can type 8 pages for every 4 pages that Dan can type. Since Carl types twice as fast as Dan, he will type twice as many pages as Dan. Therefore, when Dan has typed 12 pages, Carl has typed 24 pages. So these are relationships that you have to glean from the information that you've been given. Now let's do an example. If there are 3 cars for every 8 students at a high school, how many cars are there for 1,200 students? Now what we can do here is we could set up a proportion. So notice if there are 3 cars for 8 students. And I'm a big fan of writing the units in so you can get the ratio or the proportion set up correctly. So 3 cars for 8 students. How many cars are there for 12 students? So again, cars goes in the numerator because that's where I put it in the ratio to the left. And we don't know how many. I'm going to call it X. And then 1,200 students, which is in the entire high school. Now when you solve it, you can of course leave the units. 3 over 8 equals to X divided by 1,200 or 1,200. And remember the rule, a proportion is true if you can cross 3 times 1,200 and set that equal to cross this way 8 times X. Now I want to get the 8 by itself, so what do I need to do? I need to divide both sides by 8, and that will give me the result X is equal to 3 times 1,200 divided by 8. This does make me want to grab my calculator. I know you could do this by hand, but let's just use our calculator. And I get the result 450. 450 what? Okay, so how many cars are there for 1,200 students? It would be 450 cars for 1,200 students. And if we review the typed up result, notice they put cars over students just like we did. And you have 3 over 8 equals the missing value. We don't know how many cars are associated with 1,200 students. And then the next step, notice they cross multiply. That's what that's called, 3 times 1,200. Don't forget your equals in the middle equals to 8x. And then they go on to solve. That gives us 3,600 equals to 8x. And when you divide 3,600 by 8, you get 450 cars associated with 1,200 students. Now, whenever you have a proportion, you have a constant of proportionality. If the variables x and y are related by the equality y is equal to kx, then k is equal to y over x, and y is proportional to x, and k is the constant of proportionality right here between y and x. Now, a super simple example of that would be to say if Carly, I'm just going to use a C for that, runs twice as fast as Buford, then our constant of proportionality would be 2. Okay, so that's the constant of proportionality. So say Buford runs 5 miles per hour, then 2 times 5, Carly runs 10 miles per hour. Now, a central idea in proportional reasoning is that a relationship between two quantities such that the ratio of one quantity to the other remains unchanged as the numerical values of both quantities change. In other words, that constant of proportionality stays fixed, so it doesn't vary in one situation or another. Carly's always twice as fast as Buford. Basically the example I gave before. So there's a constant between the two. Now, we want to use the scaling strategy, which we haven't covered yet, but don't worry, you'll see it in this problem, to determine which is the better buy. 12 tickets for $15 or 20 tickets for $23. Now, the scaling strategy for solving the problem would involve finding the cost for a common number of tickets. So you're looking for the least common multiple of 12 that represents the 12 tickets and 20. And it turns out the least common multiple for 12 and 20 is 60. So we could calculate how much 60 tickets would cost in both situations. So let's do that. So if we bought 60 tickets for the rate of 12 tickets for $15, we know that 5 times the 12 tickets would equal the 60 tickets, right? And that would be 5 times $15, which would cost us $75. And we're going to do the same thing with the 20 tickets, but this time it would be 3 times the 20 tickets would equal the 60 tickets. And that would be 3 times the $23, and that would equal to $69. Now, you compare $75 to $69, and you see that the better deal is definitely the $69 or the 20 tickets for $23. And of course, I have this typed up. So in the first plan, since 12 tickets cost $15, then 60 tickets cost $75. And in the second plan, since 20 tickets cost $23, then 60 tickets cost $69, just like we calculated. And so we see that the second plan is the better buy because it is $6 cheaper for 60 tickets, even though we don't plan to buy 60 tickets. That is the scaling strategy to solve this problem. Now, I would tend to think more along the lines of the unit rate strategy, and likely this is what you thought too. Use the unit rate strategy to determine which is the better buy, 12 tickets for 15 or 20 tickets for 23. So once again, the same exact problem, but the unit rate strategy for solving this problem involves finding the cost of one ticket under each plan and then comparing the cost. And this is probably the way that your brain thought of handling this. So let's calculate for one ticket. So if 12 tickets cost $15, couldn't we take the $15 and divide it by 12 to get the cost of one ticket on that plan? Okay. So 15 divided by 12. Now don't worry about changing that to a decimal. Remember, we haven't discussed decimals yet. But this is just a ratio. Let's put it in lowest terms. So 15 over 12, they both divide by 3. So you could change that to 5/4. Now we're going to compare that to the other plan, which is 20 tickets for $23. And we set up 23 over 20. And we reduce that fraction, which actually doesn't reduce. Now, we need to compare these two fractions. So, with two different denominators, how could we possibly compare these two fractions? Well, how about let's find a common denominator, right? So, I'm going to multiply this fraction by 5 over 5. And that's going to give me 25 over 20. So which one looks cheaper? Well, again, we knew that the 20 tickets for $23 was cheaper. And when we compare 23 over 20 to 25 over 20, we see once again that the 20 tickets for $23 is cheaper. Now, I've got that typed up for you. So in the first plan, since 12 tickets cost $15 and one ticket cost $1.25, notice I didn't do that. I put it in fraction form because we haven't officially discussed decimals yet. In the second plan, 20 tickets cost $23 and one ticket cost $1.15. So the second plan is a better buy. Now, would I get you because we haven't discussed decimals yet? Because in theory, we could still talk about money. No, that's perfectly reasonable. Again, I left it in fraction form, but notice I do have that. If we did 5 divided by 4, that is $1.25. 23 divided by 20 is not quite as obvious, but I'll agree that's $1.15. And it does make it a little bit clear when it's in dollars and cents. All right, so I have another example for you. We have Kai, Paulus, and Judy. They made $2,520 for painting a house. Kai worked 30 hours, Paulus worked 50 hours, and Judy worked 60 hours. So clearly they should not get equal pay, right? They divided the money in proportion to the number of hours worked. If they all earned the same rate of pay, how much did each earn? So how could we handle this problem? Now my thought is, why don't we take the hours that they worked? So we've got 30 hours plus 50 hours plus 60 hours, which gives us a total of 140 hours. And then we have this amount of pay. So 2,520, right? And we write that as a ratio over 140 hours. And we can find out your pay per hour, right? Because we have pay on top and hours on the bottom. That's our rate, pay per hour. And we might as well just start using these decimals because we're dealing with money. So I've got 2,520. We're going to divide that by 140, and I get $18 of pay per hour. So how could we pay each of them? Well, because Kai worked 30 hours, we would multiply 30 times the $18. Since Paulus worked 50 hours, we multiply 50 times the $18. And then Judy's the one that worked the most. She worked 60 hours, and we would multiply 60 by $18. And we could check ourselves how? Well, after we got each of these values that they're going to get paid, what should that total up? Well, 2,520. And as you know, I've got this typed up for you, so let's take a look. It says, let X be the unit rate or the rate of pay per hour. Then 30X denotes the amount of money that Kai received. It's a little different than what we were thinking about. And then 50X denotes Paulus. And then 60X denotes Judy. And we could add the 30X plus the 50X plus the 60X together. Now what do you expect? Well, that's going to give us that 140X that we talked about. And you set that equal to 2,520. And we're going to get $18 per hour, which is exactly what we did earlier, but we didn't use any algebra to do it. But it's very efficient to use the algebra. And then you would go back and plug in. Again, 30 times the 18 is 540 for Kai. 18 times the 50 is 900 for Paulus. And then Judy is 60 times 18 is 1,080. And remind me, what should that add up to be? The original amount of money, which was 2,520. Now what do we have here? For any rational numbers, A over B and C over D, with A not equal to 0 and C not equal to 0. And we also know B and D are not equal to 0 either, right? Because if it's a rational number, B and D can't be 0. Okay? Now, let's break this down. It says A over B equals to C over D if and only if, what did they do? They wrote this as B over A and D over C. What has happened between here and here? We flip both of the fractions. Is that allowed? Absolutely. So proportions, there's more than one way to write them. A over B, C over D is the same thing as B over A and D over C. If you flip one, you have to flip the other one. But it's more than just that. So once again, this is our original proportion, A over B and C over D. Oops, I circled the wrong one. Here's our original proportion. A over B equals C over D. Watch what happens here. Notice they put A over C. Okay, and then B over D. You could also, they don't have it included, you could put C over A and D over B, which is really a combination of both of these ideas. All of those would be true statements. Ratio and proportions are used in scale drawings. The scale is the ratio of the size of the drawing to the size of the object. Now I have an example for that. And here you go. It happens a lot with floor plans and blueprints, or you're looking at maps. Is no way to draw that to scale, so they have what they call a scale drawing. And notice the scale here for this particular problem. We have a floor plan of the main floor of a house, and the figure is drawn to a scale of 1 to 300. There we go. There's the pen. Okay, 1 to 300. It says find the dimensions in meters of the living room. So here's the living room. We're supposed to find the dimensions in meters of the living room. And if you'll see, they give us 3.7 centimeters is the length of this vertical line. 2.5 centimeters is the length of this vertical line. Now, this is a scale of 1 to 300. So the actual living room is 300 times the size of what's been given. So this is the 1. So we're going to take 3.7 and then we're going to multiply that by 300. And for the bottom, we're going to take 2.5 and multiply that by 300. Again, officially, we haven't discussed decimals. So we're just going to have to go on our current understanding of decimals. 3.7 times 300. And that gives me 1,100. I'm sorry. Yeah, 1,110. 1,110 what? Well, centimeters, right? Because I took centimeters and I just multiplied it by 300. We multiplied 2.5 times 300. That's going to give me 750, again, centimeters. Now, if you read your problem, notice they want the dimensions in meters, okay? So if you convert centimeters to meters, remember what you have to do? You have to divide that by 100. So we have 11.10 meters is the length here. So this is 11.10 meters. And here, again, 750 divided by 100 to change it to meters would be 7.50 meters. 0 not required on either of those. Okay, so we have the ratio of 8th graders to 7th graders at a meeting is 4 to 7. Now, for part A, it says 1/4 of the 8th graders were boys and 2/7 of the 7th graders are boys. What is the ratio of boys to students at the meeting? So let's handle that first. So question A. Now, the point of this question actually is not necessarily to do it by hand, but to show you a model. The pages got out of hand, I apologize. It's to show you a model, but we're going to do this by hand first. Do the math first, and then I'll show you the model. So 1/4 of the 8th graders. Now, again, let me remind you, this is 8th graders. So 8th graders to 7th graders. And the ratio they gave us was 4 to 7. That's just people, okay? But then it says 1/4 of the 8th graders are boys. Okay. 8th graders is on the left. 1/4 of these people are boys. Okay. Then it goes on to say, we keep going with this, then also 2/7 of the 7th graders are boys. Okay, so let's look at the 7th graders. 2/7 of the 7th graders, which happens to be 7 in our ratio, are also boys. Now let's do each of those calculations. We know 1/4 of 4 is 1. We'll just put that right here. 2/7 of 7 is 2. So in our ratio, there's 1 out of 4 boys for the 8th grade, and then 2 out of 7 boys for the 7th grade. Now, total boys, that would give us 3 boys. 2, what's the total number of people? Well, 4 plus 7 would be 11 people. So, again, boys to total would be the ratio 3 to 11. Now, if we keep going, question B says, if there are 9 boys at the meeting, what is the total number of students? So we've got 9 boys. Remember, this is 9 boys. Over here is going to be total number of students. Now, if we keep this same ratio, because this was 3 boys to total, then notice what we've done is we've multiplied by 3 over here. So we would be required to multiply by 3 over here also. So that means there would be 33 students total. Okay, now that's not the only way to handle this problem, but it seems to be the easiest to me to think about it that way. All right, now let's look at the diagram that we're given. So a bar model of the situation is shown. Now let's see what's going on here. We've got 8th graders. Notice they put 4 to represent our 4 to 7. So again, 4. Oh, come on, pins. So we've got 4 to 7. You can even count them if you need to. It's separated right here. The 1, 2, 3, 4 is 8th graders. 1, 2, 3, 4, 5, 6, 7. Okay, is the 7th graders. That's the original 4 to 7. And then what's highlighted, right, 1/4 of the 8th graders were boys. So 1 out of these 4, that's the yellow, were boys. And then 2 out of the 7, again, yellow, were boys. All right, it says the ratio of boys to students is 3 to 11. Remember, that's what we figured out earlier. So 3 to 11, where did the 3 come from? That's the 3 yellow that we have here. And then where did the 11 come from? Well, 11, remember, is the 4 to 7. There were 4 8th graders, 7 7th graders. Okay, and remember, this is just a ratio. So that would be out of 11. That's not necessarily how many people we have. Again, that's just a ratio. And you can look at the picture and tell it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 represented there. Now part B, it says if 3 units is equal to 9, then 1 unit is equal to 3. Therefore, the total number of students is 33. Now, to me, that's a little bit confusing. You might see that better. I just had to think about turning 3 into 9, so we multiplied by 3. So again, to turn 3 into a 9, we multiplied by 3. So to turn 11 into what it needs to be, we also have to multiply it by 3, and that's where the 33 came. So they're thinking the same way, it's just typed up. So that is my entire presentation of section 6-4 dealing with proportion. Hopefully you will get through the homework of ratio and proportion without too much trouble. But if you find any difficulties, you just reach out and let me know, and we will go from there. Hope you have a wonderful day.